Mukund back again to give us yet another quantum spacetime seminar. Mukund.
Okay, so thanks, Shiraz. I'll talk about string partition functions in AdS3, which should appear sometime in the next couple of days with our former postdoc Christian Ferko and Samir Murthy. And much of the ingredients that go behind this talk are, at least to some members of the audience, very well known. They're sort of ancient knowledge in AdS3, but there's some aspects of it which I felt were never really clarified, and one of the things we'll try to do is clarify them. But there were three sort of broad motivations why we sort of wanted to look at this. The first was related to near-extremal black holes in string theory. So we've known for a long time that black holes can, in various dimensions, attain extremality bounds, and at extremality, naively, classically, the black holes have non-zero area and therefore non-zero Beckens and Hawking entropy, which is at odds with the quantum properties because they're also at zero temperature. And in the last 5-6 years, it's become clear that as long as there's no supersymmetry reason, such black holes actually don't really have macroscopic degeneracy. The low temperature entropy gets corrected by the presence of some nearly zero modes in the near extremal geometry. And the way people realize how this works was by working out the one loop determinant a bit more carefully than what had been done before, taking into account the regulated one loop determinant of these zero modes. Since this is a feature that's visible in semi-classical gravity, you might ask what happens at finite string lengths. And a priori you might expect that such features should persist, and you should like to see this from the worldsheet construction directly.
The near extremal because they're rotating or because they're charged?
The example I will discuss will be because they're rotating. So but in general, you might ask this question more generally in various black holes, supersymmetric otherwise. From the
worldsheet. Interesting. Is that this is one example where these near extremal black holes, when they're rotating, actually exist as stable black holes.
Exactly. So
high areas
they don't exist. Right. The second motivation was to understand the asymptotic symmetries, which is not unrelated to the previous point, in AdS3 and the associated boundary gravitons. From the partition function. Of course, from canonical quantization, the very first paper in the subject by Givian, Kutuzov and Seiberg actually constructed vertex operators for the boundary currents and explained how the Brown-Hainaut Virasoro algebra arises from the worldsheet. But it would be nice to sort of organize the spectrum directly from partition function in terms of these representations, in terms of the boundary representations. Put differently, there is a calculation in semi-classical gravity of the one loop determinant around AdS geometry, a calculation that was first outlined by Maloney and Witten and actually carried out using heat kernel techniques by Gyambi, Maloney and Yin. You might ask, can you repeat that exercise, get that one loop determinant from the string worldsheet? Okay, and the answer is going to be yes. In fact, you might say it's a bit of a heavy hammer to actually try to get this answer, but there are examples with higher amount of supersymmetry, one of them which I'll discuss, which have not been sort of carried out before in supergravity, and the string theory answer is seemingly straightforward to get.
Wait, one loop determinant, you mean just of the boundary gravitons?
Or just of the boundary gravitons, yeah. But if you do it from the worldsheet, since it's not just pure gravity, you will also get other stuff. But in particular, you should see the boundary gravitons. The third is a question that's also been existed for a long time, which is what is the full spectrum of currents say in 2B string theory on AdS3 times S3 times T4, let's say spectrum of boundary currents. Okay, so what do you expect for this example? So you expect that this example preserves n equals 4, 4 superconformal algebra. So it has a set of supergravitons and super partners of the supergravitons, and the n equals 4 algebra has SU2 R symmetry, so you expect an SU2 current algebra generators. But because it's a T4, you also expect in the NS sector 4 holomorphic and 4 anti-holomorphic U1 currents plus their superpartners. Okay, these just come from dimensional reduction of the B field and the graviton on T4. However, if you look at the Ramond sector, you expect an additional 4 U1 currents and their superpartners. Okay, so this was worked out by Givian and Kutazov and Seiberg, and they noticed something curious. They noticed something that these currents don't seem to exist. They don't seem to be vertex operators corresponding to these currents. Okay, so this part of the discussion, some aspects of the discussion actually are very nicely discussed in a recent paper by Aharoni and Urbach, and one of the results I'll mention to you was we do not also see in the world sheet spectrum analog of these Ramond currents. So the question from a dual CFT point of view would be whether the dual CFT is symmetric product of T4 plus an additional T4, or is there, and if there is one, it sounds like this additional T4 is just decoupled, it doesn't talk to the symmetric product.
So when in type 2B?
When in type 2B. It doesn't actually matter because this is T4.
Yeah. So let me think in type 2B.
Yeah.
Then there is a two-form potential, Ramond potential.
Yes.
And that on the cycles of the torus give you these additional gain.
Sorry, you're in 2B. Yes, that's right.
Okay.
Yeah. That's exactly where they got it from. I mean,
yeah.
I think Kutazov Seiberg actually worked this out in 2A language because it's a bit easier. There are no self-dual things to worry about, but same thing. Okay, so this is what I want to get to, but I want to point out a couple of puzzles right at the beginning, and a puzzle that's been bothering us for quite a while now. We tried constructing the partition function on AdS3 times S3 times K3, which you might think is very straightforward because K3 can be realized as T4 mod Z2, okay, by a standard orbifold construction. And now there's a distinction between 2A and 2B. 2A preserves all the 2B preserves all the supersymmetries. 2A breaks half of the supersymmetries. 2A is dual to heterotic on AdS3 times S3 times T4. So there must be two independent partition functions, whereas here there's only one which preserves 4, 0, one which preserves 4, 4. We go through the exercise of constructing the orbifold, and we find that there does not seem to exist a partition function respecting spacetime supersymmetry. I must emphasize that this is a problem of constructing the partition function. If you do canonical quantization and actually work out vertex operators, there is actually no problem. You can actually see all the states explicitly. And I'll explain why there's an issue here when I get to it. Okay, but I just want to highlight this as a puzzle that we don't know the answer to.
Let me ask a probably stupid remedial question. So all of these currents
Yeah.
appear as boundary currents.
They all appear as boundary currents.
And then you can make multi-particles of these and get the whole module.
Exactly. Yes.
So that module just lives at the boundaries.
That's right. That's right. So there's a module that lives on the boundary, but there's then there's the heavy string states which live everywhere, and they also live in their modules. Yeah.
And that explains why every state appears in a module.
Exactly. Yes. And to some extent, that's a new thing that we tried doing, which was sort of implicit in the discussion of Malasen and Nuguri, which I'll describe in a moment. They're the first people who wrote down the partition function, but they didn't. To a certain extent, they didn't bother to write down the answer in terms of Virasoro modules, but and that led to some confusion, because when we were looking at this initially, I thought it surely must be true, because Givi and Kotaza-Saiberg already have constructed the vertex operators, but it wasn't obvious, and post facto it wasn't hard, but it sort of was something that should have been done a while ago.
Let me ask you one other probably very stupid question.
Yeah.
Like the vacuum module is annihilated by N-1.
Yes.
Whereas other modules are not.
Yes.
How do the boundary gravitons see that difference?
BC goes, I'll tell you. But yes, the short answer is BC goes. Okay, okay, so let's actually just start. So let's start with the bosonic theory, where we'll see all the features, and then we'll do supersymmetry. So here I'll just take AdS3 times some CFT x. So AdS3 will be described by an SL2 level KWZW model, and it has central charge 3k over k minus 2, and x has whatever central charge it needs to make it critical, and if you want x to be a compact unitary CFT, k needs to be bigger than some number 52 over 23, but I'll actually take k bigger than 3. Okay. So k and in particular for most of the discussion, I'll actually take k strictly bigger than 3. At k equals 3, there's an infinite tower of higher spin currents that emerge from the continuum series representations. I'll say what they are in a moment. So this was described by Gabardiel, Gopakumar and Hull 5-6 years ago. And what we're going to try to do is we're going to take AdS3, the Euclidean geometry, and identify the Euclidean time circle and the angle as we go around by a thermal period and a chemical potential for rotation. Okay, so which means that this AdS3 geometry has a boundary which is the torus with modular parameter which I will call tau, and I'll take this is the space-time torus, and on the world sheet there is also another torus whose modular parameter I will call T, and I am looking for maps from this world sheet torus into AdS3, in particular wrapping this boundary torus. Okay. So when I write formulas later, I will write z to be e to the 2 pi it, and here I will write q to be e to the 2 pi I tau. Okay, so I've sort of flipped the usual convention. tau will refer to the boundary, not to the bulk.
The factors of I, when we normally do torus compactification, we move by a real amount in the position.
Yes.
And that gives us the real part of
Temperature is up.
Temperature is up, that's imaginary.
That's imaginary.
And moving by real amount in x gives us real part of tau. Since you move by complex part in
Phi.
why?
Euclidean. It's rotation. It's rotation in Euclidean signature. It's JT phi. Yes. In Lorentz signature, it will be plus beta mu.
Wait, let me ask again. In Euclid, sorry, just because I'm stupidly confused. If I just an ordinary torus with x and t,
yeah,
and I in Euclidean,
yeah,
and I move x by some amount,
yes,
that is what is the real part of tau.
Yes.
And the time part is the imaginary part of tau.
Yes.
So if I move x by a real amount in Euclidean, that gives a real part of tau, and if the time part is the imaginary part. So what was confusing me is that you move phi by imaginary thing in Euclidean, and got that part, the mu came with real.
Well, this is what you said before. This is the picture of the torus, because the torus is tilted. If the torus was straight,
yes,
then it would be just thermal identification, just imaginary.
Yes. Then you move it like this,
and that's the torus. That's the torus.
Yeah, but isn't that phi goes to phi plus beta mu? Why I? Why the I?
Yeah, go ahead.
The progress is phi plus I beta mu, and the beta mu is in you go down, the beta mu doesn't have I in the tau.
Yeah, that's what he's saying. But but if I think about it as the angular momentum component, angle generator mt phi in Lorentz signature,
yeah,
then there's an I in Euclidean signature.
So in Lorentz signatures, I j mu, right?
No, it's plus. Yeah, it's e to the minus beta e minus mu beta j.
J, correct.
So that's why there's an I in Euclidean signature.
That's an I. Okay, I need to think. Please.
Okay, but it's, if you think about electric fields, same thing, right? Chemical potentials are imaginary in Euclidean signature. I think this is correct, but
I agree that the chemical potential is imaginary Euclidean signature. That part I agree.
yes,
What was not clear to me was that translates to a real part.
plus here.
Yeah.
Okay, let's take this offline.
Yeah.
Okay. So now I'm just going to give you the answer, because this was worked out by Mallasina and Oguri for the partition function. So the partition function is going to have three pieces. So we just need the bosonic string partition function on AdS3 times x. So there's going to be a piece which is the SL2 partition function, which will be a function of, okay, this one will be a function of t bar, tau bar. There will be partition function of x, which will be a function of t and t bar, and there will be the BC goes, which will also be a function of t and t bar. Okay, so these are the three pieces we need, and we can write down three pieces separately. And then this guy needs to be integrated over the worldsheet modulus, worldsheet torus over the fundamental domain. So, okay, and the measure is just this. Okay, let's write down these three pieces first. Let's do the BC system first. This guy is easy. Okay, it removes two like directions in the holomorphic and anti-holomorphic side, so it gives you eta tau to the 4. This guy, I'll make no assumptions right now, so I'll just say it's some it has some ZZ bar expansion of the following form. For simplicity, I'll assume that this CFT is generic and that it has no conserved currents. Okay, so it has no chiral operators, but you can sort of, I'll later talk about examples where there are chiral operators, so you'll see what happens there.
And every object here is modular invariant in T.
Every object here is modular invariant in T. Actually, this isn't.
Yes.
Right? This isn't, but this isn't precisely because this isn't, and they work out correct.
But ZX is modular.
ZX is modular invariant.
Yeah.
And ZSL2 also is modular invariant. So let's write down this guy. So let's first, before I write this down, let's see what ZSL2 looks like. So first of all, I have a worldsheet torus, and this torus is trying to wrap around, well, actually let me draw one more picture here. AdS3, where this is identified, time is identified with beta, and as I go around this identification I also twist in the angle, okay, which means that both the cycles of this torus will wrap around this time Euclidean time direction. So there will be two, I'll think of them as two winding numbers, and therefore this partition function is parameterized by a double sum over two winding numbers. So let's write down that answer.
And because phi is contractible, there's no winding sum.
Because phi is contractible, there is no winding, but that winding, it will show up because it is twisted. The winding along T is twisting along phi.
But the number of sums is just
two. Right. If there was an actual torus in the bulk, then the number of sums would be 4.
Yeah.
Okay, so I'll write down various pieces. Okay, I'll explain what this UNM is in a second, and then because of the winding, you get the usual factor from winding which is basically the solitonic energy of a string going around a single direction, and then there's a piece which is sort of not obvious, but I'll tell you why it's there.
Denominator is the oscillator.
The denominator is the oscillator. So I'll explain these two factors now. So this piece by itself is just the usual answer for a compact boson, and if with an extra factor of actually as it is in this notation with a factor of 1 over root 2, this thing is modular invariant. In fact, the sum is modular invariant. This UNM is this particular combination of worldsheet modular parameter and space-time modular parameter, and I've chosen a convention where holomorphic maps holomorphic. Okay, this was not necessary, but this makes life easier. And as Shiraz said, the denominator is oscillators, but this piece is there to make this piece plus the denominator by itself is modular invariant. The denominator by itself is not modular invariant. There are several ways to say what's happening here. Theta 1, we can. So what would we have expected?
I'm sorry, what was tau?
Tau is the space-time boundary torus modular parameter. Okay. So suppose.
So im tau, basically it's an im tau factor that makes up the modular invariance.
It's almost an im tau factor, but because it also has a t.
Oh, there's a t. And we're worrying about modular invariance in t or tau?
In t, not in tau.
So the im t part is what makes it.
Im t part is what makes it modular invariant, because this is also an im. T2 is, sorry, I should have said this.
The usual.
T is t1 plus it2. Okay, so it's AdS3, so it roughly has 3 directions. It's like, okay, so if you decompactify it, it would be R3, and then this would have been eta cubed, right? But see what's happening. So first of all, it's like a compact boson, and what is theta 1? So theta 1 of nu t is okay, let me call this t. Let me just use this notation. Okay, that's the infinite product representation. The z to the 1/8 is just the fact that there are 3 bosons, so it's sort of the basic energy, vacuum energy is 3 times 1/24th. This piece is because theta 1 doesn't have a 0 mode. You recognize theta 1 inverse in the numerator as a Raman sector trace for periodic fermions. And when I put this elliptic parameter tau to 0, Raman sector trace is 0. That's exactly what's happening here. When q is 1, that thing goes away. Okay, usually you'll see this as one factor of n minus 1 removed. That's okay. And keep track of this factor for now. This factor is nice. It sort of says something useful. And then this is one oscillator, which you can think of as oscillator corresponding to, roughly speaking, the radial direction in AdS. There's a way to write AdS. I'm not going to write those coordinates. I wrote sort of nice coordinates that are conventional. But there's a way to write the SL2 group element, where this twist basically, if you think of SL2 as one radial direction and 2 angular directions associated with the boundary, then this twist basically takes one of the J plus generator of SL2 and gives it charge +1, and takes the J minus generator of SL2 and gives it charge -1.
So of the 3 bosons, 2 are twisted and 1 is not.
Exactly, and the twist is by the boundary modular parameter, and that's exactly what this U is doing. So U is a twist, and basically it says that you get twisted bosons with chemical potential set by this UNM. Okay, so this is the piece that Malasen and Oguri had written down in their paper, and it was, I think, first worked out by Gavetsky in the 90s. But this whole thing is modular invariant, and now we are left with the following task.
So very roughly, should I think of it as that bosons are along the T and the phi direction are twisted, and those along the radial
direction are not twisted. Exactly. Yeah. Exactly. Because the radial direction is like, the radial direction actually is what gives you this factor, because it's non-compact. It's almost like a non-compact boson.
And just doesn't participate in the twisting.
It doesn't participate in the twisting because you go around and you twist and you don't do anything else. Okay, so we are supposed to do this integral. If you do the integral, then the question is, so let me write this as z worldsheet. It's a function of tau and tau bar. Okay. Once you've done the integral, then you have to reorganize it in terms of in terms of characters of the boundary Virasoro symmetry. Okay. So first of all, something that should have been done long ago but didn't get done is that there is an explicit factor of q to the half minus q to the 1 minus half here. Okay. So which means that that q here is basically UNM in some sense.
Let me understand that factor.
Yeah.
Like the explanation you gave was from fermions.
From fermions, yes.
The Raman sector, there it's very clear.
There is very clear.
In the boson situation, why do you have these?
Because there is the better way to write this is to write some factor of q to the half and remove 1 0 mode. Then it's clear that it's not there. And see, this is precise in the fermion case. It's precise as 0 mode.
Right.
And I just wrote it sort of in a different way to make that manifest.
But can you understand physically why the bosons go? So theta is infinity then, no?
Theta is 1 over theta is infinity.
So some field goes massless.
Yes.
What is that?
Well, eventually it's not going to do that, right? Because that would happen when q goes to 1.
Yeah.
But for q going to 1,
I see.
that's a sort of zero temperature limit. Infinite temperature limit. So you have a regulator in the problem. So you're going to prevent it from getting there. Okay. So as Shiraz pointed out, everything here is now with these factors, it's modular invariant. So we can play this trick that so what we have to do is integrate in the t-plane over the fundamental domain of the torus. Okay, but this is a somewhat awful thing to do, but we can do the following. So we have this double sum over these two windings. We can unwrap this to the integral over the entire strip with the sum only over, in my notation, m in z, and I drop the term which is m comma n equals 0, 0. Polchinski trick, yeah. Okay? So that makes this integral nice. So t1 goes from minus half to half, and t2 goes from 0 to infinity. And then we will look at the structure of this answer. So you have a sum over m. But now look, everything which comes with m comes with m tau. M only appears multiplied by tau because everything appears with u and m appears with beta, which is the same as m tau. And so this guy looks like some function of q to the m, q bar to the m. So if you go back to sort of and think about it as follows. So the sum on m can be interpreted as Bose multiparticling sorry, this sum is over 1 to infinity, sorry, m is not over integers, it's from 1 to infinity. And so we can think of the term with m equals 1 as a single string partition function, and then think of the sum over various values of m. There's a I'm dropping some there should be a factor of 1 over m here to get this right. Then that gives me the multi-particle, multi-string state configurations. Because I'm actually computing an off-shell partition function, I should compute this partition function over all multi-string configurations.
I'm getting very confused. Sorry. Just in the flat space example.
Yeah.
This guy goes up in the exponent, right? This.
So good. So this is the string. I wrote this as world. Yeah. So the CFT partition function of tau bar is, I think this is what you're after, is exponential of z world sheet of tau bar. Right.
And I thought the exponentiation would do the multi-particling.
But here the exponentiation comes with already as a sum because the world sheet computes. See, the world sheet computes when you have m times beta, you're winding around the time circle m times.
Yeah.
And that could either be a single string wound m times or m strings wound once each.
Right.
And that's part of the thing, and that's indeed in the exponent, but that's because you're supposed to exponentiate the world sheet answer.
Yeah, I see. This happens even in flat space string theory?
This happens even in flat space string theory, except that there you don't know how to interpret it from some target space point of view as partition function of somebody.
It's continuum.
It's because it's continuum. Exactly. That's a difference. Whereas here, you also don't have a nice parameter, right? You don't have the analog of a boundary torus to say this is a space-time CFT partition function.
So this is a very new to me. So you're saying that Bose factor.
Yes.
It's an exponential, but it's a Bose exponential.
It's a Bose exponential.
That's
what we're getting from here. And you can check the structure of this answer is precisely written as, as a logarithm. It's written as, it's not a word I'm going to use, but there's a word for it in mathematics, which I don't like. Ask me later. You can say it. I'm not going to say it. Yes. So yes.
It's Bose exponential.
So Bose exponential. So I like the word Bose multiparticle.
Yeah.
So it actually does multiparticles. Okay. So these are nice features. So we don't actually have to look at the whole sum. We don't have to look at everything. We just look at one term, and then it's clear what to do. So we just look at the single string free energy. So that's the m equals 1 term. Okay.
So, for instance, if I look at Polchinski volume, whatever,
Yeah.
volume 1,
Yes.
I don't see this formula there, do I?
It's there.
It's there.
It's there. It's sort of there because Polchinski would say, well, he doesn't know what to expand this in.
But the sum over m and interpreted as a Bose exponential was there? I can't remember.
Yes. Actually, Polchinski volume 2 is more clearer on this because Polchinski actually does not compute directly the worldsheet, the superstring partition function. Polchinski says if we were doing point particle, we would do Coleman-Weinberg, and we write down the Coleman-Weinberg formula, and for the bosons and fermions,
Right.
and then say
Right. What he demonstrates is that it's the sum over partition functions, one for each field.
one for each
And then
field.
that one for each field can be written.
This way.
Oh,
Exactly.
fine.
Exactly.
I see.
Yeah. Okay. So I'm just going to look at the m equals 1 term, and then all this mess simplifies. So that's why, in fact, you see u01 is precisely theta tau. Okay. So in fact, it's good that I wrote the formula there. So there's some exponential piece here, and if you think about what happens here, this gives you im tau squared.
Sorry, and there was some sum that imposed level matching in his situation.
Yes. So what he so I'm coming to level matching in a second. Yes. So hold on to that thought.
Yeah.
So if I set m equals 1 and n equals 0, this term combines with this term. It shifts k to k minus 2, and the denominator becomes that theta of tau. Okay. And now we can answer your question. So I can just write it here. Okay, let me just write it here. So there's a tau to 3/2. There is a product okay, this is T bar, which has some Z series expansion, and there's some 0 mode pieces I'm not going to worry about, factors of k minus 2 and so on. Let's not worry about them for now. Okay, and then there is this exponential piece. That's it. Okay. Let's do something blind for a second, and then we'll fix it. The blind thing to do is to say, oh well, let me just expand this in a z power series. I need to do the integral over t1 and t2, z is e to the 2 pi I t. So if I expand this in power series in z, I can collect terms. One important factor. And then integrate term by term. Okay. Suppose you do that. This is a mod squared. There's some z bar pieces here. So there's a piece which is z to the h, z bar to the h bar.
I forgot what Z is.
So z is e to the 2 pi I t, and t is t1 plus I t2. And that's the variable we're integrating.
So you're expanding in Z, you're basically doing it particle by particle.
Particle by particle. Yeah. So basically, when I'm taking oscillators and expanding particle by particle.
So this is you should get a bunch of fields in AdS.
Exactly. This way I should get a bunch of fields in AdS. Okay. Notice that the BC gave 1 minus eta to the mod eta to the 4. So eta squared per for the holomorphic guy. And one of those gets killed by this guy. The other one doesn't get killed here. This is important. Okay, because I'm assuming something. If this had a free boson, then it would have killed it. But I'm not assuming that for now. So this is there. This is what there is.
Yeah. So you don't. It's killing sort of 2 degrees of freedom.
Yeah.
Only one of them
is radial direction. Right. And for simplicity, let's imagine that we just look at states which are primarily in AdS, which means that I can just set h and h bar to 0. I can look at the vacuum in X. Right? That's the simplest thing to do, but we can sort of look at everything. So now let's address this question: what happens to level matching? So the integral is an integral over T2, which runs from 0 to infinity, and then there's an integral over T1, which runs over minus half to half in the stream. So you'll get a term. So you'll get some z. So let me write z as e to the 2 pi I.
Oh, so the integral over T1 n.
Exactly. So there will be some T1. There will be some set of left moving weights, h effective, and there will be some set of right moving weights, which will care about level number, it will care about h, and so on and so forth. But it doesn't matter. At the end of the day, this constraint just says left moving weight is equal to right moving weight. And that's exactly what Polchinski would have said. This is what there isn't in the point particle. Right. Point particle doesn't know about string winding, so it doesn't know about level matching. Then you're left to doing the T2 integral. Okay, and the T2 integral is a bit annoying now because there's a 1 over T2 here in the exponent. Right. But this you can cure. You can cure by basically Fourier transforming this, writing some Fourier variable. And
that term had no analog in flat space? It had an analog?
It has an analog if you do compact bosons.
I see.
Right.
I see. Wait, sorry, what is that?
You just think of this as the effective soliton energy from binding and momentum.
Oh, that's
from the compact boson.
And the compactness here is just the temperature compactness?
It's just the temperature compactness, which is what sets the scale.
It's just the winding mode.
It's just the winding mode in temperature. In fact, this is really where, if you go look for the Hagedorn temperature of the tachyon, that's where it is. Okay. So that seems like the easy thing. Now it seems like we're all done. But there's a catch. See, Z runs from the imaginary part of T2 of T, which runs from 0 to infinity. Okay. So I can take absolute value of Q, which is e to the minus beta, to be less than 1. That I can do. Beta is positive. Absolute value of Z to any power is also less than 1. So this term is completely fine. But this term is not necessarily less than 1.
So the expansion is not good, yes.
Expansion is not good. It can be greater than 1 for some n. Okay? So we have a problem. Now, and Maldassina-Oguri dealt with this problem. In fact,
since you're integrating over Z, there will be some region where you
where you will hit the problem. So in particular, you can see what happens. So if you think of this strip, so if you start here at top at plus T2 being plus infinity, plus I infinity, you come down to beta over 2 pi. That's the first place where the n equals 1 mode starts to have problem. Then you go down to the next cell, beta over 4 pi. Then the n equals 2 term also has a problem. And then you go down to Okay, this is terrible perspective, but you sort of get the idea that for every small cell of this kind, you're going to have to expand more and more of these terms with this coefficient being bigger than 1. So of course you can do it, you just have to invert the expansion, but it has a consequence. If this, say 1 over 1 minus x expands with positive powers of x, but 1 over x minus 1, if you sort of invert it, if you expand in x inverse, it has negative powers of x.
And you have to do the integral in 2 parts, right?
Exactly. And I have to do the integral piece by piece in every piece. Okay? So long story short, Maldacena-Uguri basically said, well, we'll do that expansion. They sort of more or less what everything I said is in their paper. They said, let's do this, and then just collect terms. They were completely blind to all the organization in boundary CFT. So they just expanded everything, collected all the powers of z, and argued that what they got was consistent with their worldsheet answer, what they had canonically quantized. So let's think of.
So now this breaking out of the integral into 2 parts makes it not quite field by field in AdS, right?
No. Well, but it does in some sense. You'll see.
Okay.
Okay. So I'll look at intervals of this form, right? And by W, at this point, it's just some auxiliary parameter that I introduced. Okay. Now, there's something that's nice to know, which is Maldacena-Uguri argued in their first paper that the spectrum of strings in the SL2 WZW model includes not just the usual representations of SL2, which are the discrete series and continuous series, but also all their spectral flows, which are parameterized by an integer. Okay? Here you see a parameter which is a positive integer, which in some sense you should map this parameter W to the Maldacena-Uguri spectral flow parameter, and in fact what it says is that the spectrum, this answer, becomes a sum over sectors labeled by W, which are the spectral flow sectors of SL2. I don't know how long I'm going to go on. I'm at an hour.
Free to.
Okay. I'll later come when I do the superstring. I'll write down a similar answer, and you will see that the SU2 WZW model also has a θ1 in its denominator. Okay, but SU2 WZW model is a compact WZW model, so spectral flow just shuffles states around itself. It doesn't generate new states, and you'll see why when I write down that the partition function there. Whereas here it actually generates new states because there are poles in this integrand. There are poles when q inverse z to the n hits 1. Okay, so here's the Maldacena-Uguri trick, and we'll supplement it with one other nice trick which I learned from Samir, who learned it from Zagier. So we are going to do the following. First of all, the right thing to do here is to basically do the expansion of this infinite product correctly. Okay, and I'll just make a formal statement, and you can ask me later that expansion is organized in this infinite double in somehow in terms of the spectral flow sectors, because you expand. So 1 over θ1. In fact, the thing that's nice to expand is eta cube of t. This guy is nice because θ1 prime at 0 is eta cubed, and this guy can be expanded in some double series, and we'll just work with it. Okay, and so I will write it in a particular way. I'll collect some terms and write this as I imagine doing the I imagine doing the T1 integral, so that takes care of all the anti-holomorphic labels. They just get correlated with the holomorphic labels. There will be some effective power of mod z, and then there is this exponential term. That's it. Okay, so once you do that series expansion, this gets organized nicely. I've just collected terms for a given power of z and z bar. I've collected terms into some Q series and organized them this way. Okay.
You still have to do the integral over T2.
I still have to do the integral over T2, but this can be done by just by writing this as some integral over something like this.
But at this stage, there's no clear interpretation in terms of fields and areas, right?
So far there isn't.
Yeah.
So far there isn't. So far there is absolutely none. Okay, so I'm just going to use some Fourier language to write some auxiliary parameter. Then the T2 integral is straightforward because it's pure exponential. Right. So there's nothing to do, so we can just do it. And then you're left with the zeta integral. And Shiraz said that at this point there is no nice picture. Okay, so let me rewrite this above. So there is a sum over W. There is some power of Q bar. Okay, this is just aesthetics, and then this mod p squared, let's say, then 1 minus q. And then there is an integral over d zeta, and this runs over the real line, and you'll get some integral of if I put all the factors correct, let me write it like this. So this is from the bottom end, from the top end, and then the similar term from the bottom end. Okay, this numerator doesn't care about it, but the denominators care about which end I'm computing. Okay. So this has some W dependence, which I'm suppressing. Okay.
I should have asked before. N
Yeah.
effective is what?
N effective is just, I have just collected all the powers of Z. You know, maybe from here, from whatever came out of the expansion, and I've called it N effective. So you can think of it as effective oscillator number plus the excitation in the internal CFT. In fact, if you want to write it in a particular way, you can even do what Mulder and Augurian do and write the strip off a factor here, which is the power you get in the W spectral float sector. And then there's a vacuum energy. Okay, because this is bosonic string, there's an effective vacuum energy that you have to actually keep track of. Right. So this is the piece that if you stare at the canonical quantization, it's exactly the piece you'd see in oscillator answer. Okay. So now here's the magic. See, the zeta integral is from minus infinity to infinity, but the denominator of the zeta integral has poles. Okay. And in fact, there are poles at imaginary values of zeta, right? So if you shift the contour up from the real axis and cross the poles, you'll pick up residues. When you pick up residues, there's some magic in this formula that this whole thing will become some nice power of, it's e to the minus 2 beta. E to the minus 2 beta is just mod q squared. So we'll pick up some effective q bar to some power. and then you're left with a continuum integral. Okay, so if you do this, this becomes f discrete q bar plus f continuum q bar. And think of f continuum as an integral over the zeta, or let's think of zeta as, I can tell you what the shift is. And then you can think of this S as some continuum label. But this is very nice, because now this guy basically says that you have a spectral density which is some function of whatever is remaining. All the zeta dependence now becomes some S dependence, and of states with energies which also depend on S.
Sorry, so discrete is from the poles?
Discrete is from the poles, which I haven't talked about.
Okay. And the continuum is from
From
the contour?
But the horizontal part of the contour is after I've gone out.
Gone high.
I've gone high.
Okay.
Okay. And what I pick up in the discrete depends on which sector I'm in. It depends on W. Likewise, this also depends on W. I'm suppressing that. But the function here effectively only contributes to a spectral density. The energy is whatever is an exponent. And you see the energy is quadratic in S. And this is exactly the formula you want to see for this continuous series representation of SL2. Okay. So this is the unfortunate feature of the NSNS string on AdS, that there's a continuum of CFT states, and my prefactor has this. I already have this prefactor outside. Okay. Okay, so we'll interpret all of that now. And here you just get some factors, which is q to the h CFT, q bar to the h CFT bar divided by 1 minus q squared, where there's still some sum over the w's, and these h's depend on various parameters which I'm not writing. Okay. And this is how, from the world sheet, you see the discrete states sector by sector and the continuum state sector by sector. Let me put this 1 minus q squared here, so then we can interpret it. So remember, I told you that what you're supposed to do is take this, take it as a function of q to the m, which is finish the multi-particling, which involves exponentiation. Okay. So if you take any one of these guys and multi-particle it, it will actually give you the right character of a massive representation of Virasoro.
So SL2R character will come out.
No, Virasoro character will come out after multi-particling.
I see. I thought you will need the boundary gravitons for that.
For massive character, we'll do the boundary gravitons in a second, but for a massive character, it's already clear that you'll get something that you won't recognize as a Virasoro character, what it is. Let's just do it. So you have q to the m h, q bar to the m h bar over 1 minus q to the m q bar to the m, sum m from 1 to infinity 1 over m. Okay, so flip the sums. I'm being sloppy about a sign, then this will give you log. Okay, so you basically get e to the minus log sum 1n 1n2.
Just your starting point, I'm trying to understand.
Yeah.
So you've got some state in the bulk.
Yes.
This is h bar was the
effective weight, the field.
The the field,
Yes.
and you're looking at all its SL2R descendants? Or not?
Yes. So the sorry, I think I understand what your question is. The SL2R descendants are the 1 minus q squared.
Yes.
Yes.
And that's
when I go to the
m equals 2 or whatever.
m equals 1 gives you that.
I see. Yeah. Oh, but you have all these others.
Yes.
And where did they came from? They came from.
I never took out this factor from theta 1.
I see.
So theta 1 supplies a factor
I see.
that actually
is
knows
clearly
that clearly is Virasoro. Correct.
I see.
Okay. But you're asking something very important. Which is where are the boundary gravitons?
Yeah.
Yeah. Good. So where do we expect the boundary gravitons to be? Okay. And in fact, if you want to do the boundary gravitons, all of this is overkill, because they should be first of all in the identity of the internal CFT. They are universal part of AdS3. They shouldn't care about spectral flow, so they should be in the W equals 0 sector. So we should just look at what happens in the W equals 0 sector. But that sector is trivial, you just expand. Okay? So now what I hid for you is these factors of what these polynomials are doing. Okay, so let's look at what happens in the W equals 0 sector. Write this properly. Is one factor which I don't remember off the top of my head. Okay. Okay, this is just me having done some algebra. These are the low-lying states in the W equals 0 sector. You can think of this as coming from these 4 terms, come from z to the 1, z bar to the 1. This state comes from z bar to the 2. So in some sense, I have collected the terms and I have sort of expanded these polynomials. In fact, you can just, if you want 1 power of z and z bar, you can just stare at this. It can't come from anything except the first term. There will be 1q, there will be 1q inverse. There's a minus sign here. And that's it. And if you factorize it, it factorizes beautifully into this. So there's 1, which is the identity.
Not q.
Yeah. There's 1 which is the identity. There's q squared divided by 1 minus q, purely holomorphic. There's a q bar squared divided by 1 minus q bar, purely anti-holomorphic. And then something which is neither, which is mixed. Okay? But everything is to be multiparticle by itself separately. These are all the states.
Okay.
Multiparticle this, it will give you the Virasoro vacuum character.
Vacuum, right. Because there's no q term.
Because there's no q term. Yeah. Because the exponent starts at 2. Yeah. And it's holomorphic.
Right.
Right. Same thing here. This is the right moving character.
Okay.
But now there's one new thing. There's a state with weight 2, 2, which is the universal prediction. In fact, you can check that this whole thing comes as a single product. It just factorizes into pieces. So you can just factorize this, right? So you can just write this as 1 plus q over 1, q squared over 1 minus q times 1 plus q bar squared over 1 minus q bar. So the n equals 1 term comes as the product of holomorphic, anti-holomorphic pieces. In its expansion, it has the left moving gravitons, the right moving gravitons, and a single order 1 weight state, in fact weight 2, 2. Okay. And then if you go to higher states, they get heavier. If k is very, very large, so k is the radius of AdS in string units, then these states are very, very heavy. These are the stringy excitations in AdS. These are states of order whose energies go like 1 over alpha prime. But there's one state which doesn't have very high energy.
And what is that?
The dilaton. In the superstring, it is actually the dilaton.
So the boundary dilatons.
Well, it's the bulk dilaton. But
the boundary mode of that.
the boundary bound of that. So let's explain. Let's see what that is. If I interpret this as the boundary, yeah. If I interpret this as the boundary gravitons, this is a stress tensor multiplet. This is the anti-holomorphic stress tensor multiplet. This is like some current bilinear. Okay, so this is the operator that was written down by Virasoro and Seiberg, who identified that there is actually a universal operator that you should think of as a current bilinear. In recent discussions of TT bar, this is what in the world sheet is usually called the single trace TT bar deformation. But its weight is order 1 in string units. Okay. Okay. So this has an interpretation, which I just said. This thing is from the symmetric product point of view, it's usually what's called a single trace TT bar deformation operator, because it's really a product of a left moving current and a right moving current on the world sheet.
Yes. But it dresses everything in the bulk, right?
It dresses everything in the bulk, but for now, but if you just look at the spectrum, it's just in the CFT there's a universal weight 2 operator.
So let me get one or two things that I feel there's something I have a basic misunderstanding. So this part will give you some sort of Virasoro dressing.
Yes.
Forgetting this weight 2 thing for a moment, just the 1 plus.
This thing
Yes.
will give us a factor which is product n equals 2 to infinity 1 over 1 minus q to the n. That's right.
So it's like a Virasoro dressing of whatever you have in the bulk.
Yes.
So anything in the bulk will now become like a Virasoro character, apart from the q equals 1.
Yeah. Yeah.
Apart from the q equals 1.
Mm-hmm.
Now first thing you were saying that the nonetheless,
Yeah.
the multi-particle massive states also formed a Virasoro character.
Yes, but if you just think about how you do this in the particle limit, right? So I have a collection of particles,
Yes.
right? So and you want to compute the one loop determinant. So every particle will have its own boundary Virasoro dressing. So if you multiply determinants of state by state, you will get vacuum character.
Yes.
Left moving vacuum character. Vacuum piece will just give you left times right. But a massive state would give you a form of this, an answer of this kind.
Actually, let me understand that better. I'm sorry.
Yeah.
Something elementary that I should understand. I had thought, and I think you're correcting me, I had thought that whatever happens in the bulk will only be an SL2R.
Yes.
And that to make Virasoro you need the boundaries.
Yes.
Are you saying that's not true?
That's what's happening here, right?
That's what's happening. So what was the statement that this part itself was a Virasoro character? Was that the statement?
Well, the statement is that
Oh, it does includes this boundary stuff?
yes, because this 1 minus q is the SL2R part.
Okay.
From the bulk point of view, it's the action of left and right derivatives.
I see.
But I'm saying that every one you should just treat independently, because these are all just summed up independently in the exponent.
Fine. So whatever part of that multiparticling is the multiparticling of the boundary.
Exactly.
Of the boundary gravitons.
Yes.
And that's what's making the Virasoro.
Yes, and everything else. See, the main thing is that everything except these two guys aren't purely holomorphic or anti-holomorphic.
Yes.
Which means they're not chiral currents. They're not currents. So they'll just get some fancy thing like this.
Fine. So this whole fancy thing,
Yeah.
I can break up into parts that is the chiral currents.
Exactly.
And the other stuff.
Exactly.
and then multiplying the chiral currents with the other stuff makes it into Virasoro characters. Well, the other stuff would be in SL2R characters. Is that right?
That's right.
Okay.
I mean, but in some sense, what you can think of is once I've written the formula, whenever I wrote it like this, you can think of these as primaries of the space-time CFT.
Yeah.
But in the single particle sense, you only see the SL2R action.
Yeah.
Right. Only when you multi-particle it will you see the Virasoro.
Yeah. But multi-particling, these very special modes is totally key, right?
Exactly.
Yes.
Yes.
I
Yes.
get
Yes.
it. And one last question about
Yeah.
that. What happened to the Q? So for vacuum, of course, you didn't want a L-1.
Yes.
So the other modes you did.
I did. Yes.
And where is that?
That's precisely because the Q term here is missing.
Exactly. So that's missing. But now, when
But-
you've got a massive guy, you want it.
Yes. But it shows up, right?
Where?
See, the thing is that the Q term is special. The real thing that, so let's ask how would you remove states,
Yes.
null states from the world sheet.
Yeah.
Right? The usual story is that you would remove them because a null state is pure gauge,
Yes.
and it's pure gauge because it can be written as QB of something.
Del or something.
Yeah. But the BC goes because the eta comes with a minus sign in the exponent in the numerator, it removes states. And in fact, if I had written one more formula, I could have written this slightly better. This formula is this. Mod squared. This minus Q is a statement that is this minus sign.
Sorry, but I still didn't understand why with a non-vacuum character the Q state shows up. Let me ask again.
Yeah.
Probably very soon. If you have the vacuum character, the descendants don't have the Q state.
I see. Yes.
But if you have any other H
Yes.
as your primary,
Yes.
then the Q state exists.
Yes.
The descendants have 1 plus Q.
Yes.
Where in all this do you see that?
You see that here because everywhere else, when you think of it as SL2R guys, you have a whole 1 minus Q action.
I see.
1 minus Q and 1 minus Q bar action. No separation in the. It just shifted.
I see. You look at the higher modes and you just see.
You just see it.
Oh, so it's only the vacuum.
It's only the vacuum which is special.
Amazing.
So it's only the vacuum that's special.
It's amazing.
Everything else just works. Okay.
Okay, thank you.
Okay.
So sorry for delaying you so much.
No, that's good. So, let me say quickly how this works in the superstring because there's something else that's nice, and then I will stop. So,
Wait, if you don't mind.
Yeah.
I know I keep delaying you. But
No, it's
let
okay.
Let me ask you. So at some point, one of your original motivations was to make contact with this Iliescu-Turiachi kind of stuff.
yes,
Yeah.
I could just do it now. Very good. Okay. Now, very good. So let's do that. That's easy to do here. Okay, I just need to tell you one fact, which I'm not going to prove. Something that's obvious here is that as long as the internal CFT does not have currents, the only currents are Virasoro currents. Everybody else has non-zero twist. Okay? Okay, and then there were some states which were heavy. Okay, for large K, all but these states have energies of order at least root K. Spectral flow makes it even worse. In the W spectral flow sector, the energies are order K. Okay. So, if you think about organize this, so first of all, I should say something. We are only computing the determinant around one single saddle, thermal AdS3. Okay, so I think this by itself is not going to give you a modular invariant CFT partition function. It has no reason to. It's not going to do it. It's sort of clear. It's not going to do it. But if you think about the CFT partition function and just identify the pieces, we just argued that it has a piece which is chi vacuum of tau chi bar vacuum of tau plus sum over h comma h bar stuff, massive characters. Okay. And it's important here that none of them have twist 0. There are no chiral objects in here. So this guy looks like what we just said. Okay, let me write it like this. Okay, let me ignore the Casimir energy.
That it's in modules of the boundary CFT is obvious.
It's obvious.
That it's modular invariant will not be.
Will not be obvious, but until I do something. But at this point, I don't care because I just need to know that this exists,
Yeah.
and it's separated from this by at least an order 1 twist gap.
Fine.
Okay, that was the assumption of, in fact, before Iliescu Turiachi of Maxwell, Gauche, and Turiachi, who looked at the same kind of analysis in BTZ, but using 2D CFT techniques, and later was revisited by Sridip Pal and Chow. But basically, the question is this: this is thermal AdS. And to go from here to BTZ, I just take the S modular transformation, tau to minus 1 over tau and tau bar to minus 1 over tau bar. Just flip the circles in the boundary, space and time circle. Let me do something. So I need some, of course, if I do this and then take the high temperature limit, I'll just recover the usual Cardew formula. That just comes from this piece as usual. But let's do something slightly non-trivial. Let me take the left movers to be at low temperature and the right movers to be at high temperature. Okay. So let's do the modular transformation here. So this gives me 1 over e to the minus 2 pi I over tau. I just use the modular property of eta to write eta 1 over tau as root tau eta tau. Okay. If I take so im tau, I'll take tau to be of order beta, which is going to be large because temperature is going to be small, and tau bar to be, let me for sake of argument say it's going to small. So this term is going to 0, so this is 1, but this term is going to 1 over tau, so this gives me 1 over tau to the 3 halves times some number, but this is beta to the 3 halves. So this is t to the 3 halves.
Which is what it is.
Which is what you want to expect, which is the contribution from the Schwarzian modes to the near-extremal black holes.
So I understand for extremality you take one temperature small.
Yes.
So why did you take the other one large?
Large. So the other one is taken large because this is some kind of, I also want to get the ground state entropy, and that comes from the right movers. It's almost like in a supersymmetric case, where one sector contributes degeneracy.
There's many particles.
There's just many particles.
I see.
So,
I see. All that you care about is that the other guy was small.
yes.
Just that will give you your
Yes.
Excellent.
Yes.
So is it right that you get this t to the 3 halves as long as you take one small?
One small.
What, you do.
What I do with the other one, I get t to the 3 halves. And the important statement is that it holds even when k is order 1. There's nothing here that required me to take k large to make it semi-classical AdS.
Interesting. That's what they would have predicted because it was just came from symmetry analysis?
Exactly. That's what they would have predicted, but and that's what we would have said too, because there is no reason. I mean, you could go back to statements of the kind Ashok was trying to say 10, 15 years ago, of saying, if there was a theory of quantum gravity, for which you have some semi-classical path integral prediction, that the theory of quantum gravity should also predict it independently. Right. So if string theory was to match, it had better give us this factor. It of course gives us. Of course gives us the factor.
I was just trying to understand that. This is what they would have expected.
This is what they would have expected. Yeah. I mean, it's just that okay. There's a calculation that we have not done, which I think is a very nice calculation to do. They would have said something like, I mean, of course, if they do the near horizon analysis, they look at Schwartzian in AdS2 and so on, it's not clear how to treat that from a world sheet point of view.
Yeah.
But there's something else you can say, which is there's a prediction for the string spectrum in Lorentzian BTZ geometries. Right? It should say that there are states which contribute with very low weight to the path integral, which actually bring down the macroscopic degeneracy that you would have seen at 0 temperature. Right? So if you did a canonical quantization,
these are just the very light quasi-normal modes.
These are the very light quasi-normal modes in the BTZ geometry, right?
Yeah,
but it's because it's a long throat. But how does the canonical quantization see it?
Why does it see it as the canonical?
But nobody's done the calculation.
What?
Nobody's done the calculation in BTZ. Right. But yes. But this path integral construction says that yes, it should see it.
Yes. And can you identify it as just the very light quasi-normal? Take one massive scalar field.
No, it's not in scalars. It's importantly not in scalars because it comes from the vacuum. It comes from the boundary gravitons.
My God. Okay, so it comes from graviton. So take the graviton.
Yes. So the short answer is okay. Now you and I are going to have to debate about whether gravitons have quasi-normal modes in AdS.
That's a question. Yeah, you wouldn't have expected.
Yes, but in so what I can tell you is that if you do, there actually are eigenfunctions of the spin 2 fluctuation operator with light eigenvalues with scale like temperature.
And do these modes live near the boundary or not?
They have a, so as the temperature goes lower and lower, the modes descend down the throat.
So they don't live entirely near the boundary.
They don't live near the boundary.
So the statement that I've believed all my life that there are no gravitons in AdS3 is a lie?
Well, it's a gauge dependent statement.
You're saying that locally the modes are always pure.
They're always pure gauge, so there exists a gauge in which they're purely boundary modes.
Okay.
Yes, that's the gauge you and I like to think about always.
Yes.
And therefore you never try to compute the determinant in the bulk because there's nothing to do.
Yes.
But you can pick some other gauge.
It sounds like optics.
It is optics. but you can certainly make the modes. But wait. But the modes are off shell. If I'm thinking of eigenmodes, then there is meaning to it.
Yeah. So this is what I was missing. So off shell, it's a clear. So then my statement about quasi-normal modes
is not clear.
Wrong.
Is not clear. It's not clear to me how to think about it that way.
Yeah. Okay.
Yeah.
Thank you. That's really cool.
Yeah. So indeed. So in fact, this is my problem with the thing we discussed a few weeks ago about this Hartnell-Sachdev formula, that it's clear that it works. It gives the answer I want, but it's not clear what I'm doing, what's going on.
Yeah.
Okay. So I'm sorry, I'm not going to keep people hungry for too long. Let me just say a few things about the superstring.
I'm sorry, I should apologize since I've been delaying you like
No, that's okay. This has been fun. So for the superstring, I'll just write some schematic formula and then tell you something if you want to ask me later. So we already encountered this beast, ZSL2. But actually, let me just say what I'm going to do. I'm going to do AdS3 times S3 times. And to be sort of perverse, I'm going to allow myself, as I go around the time circle, I'm also going to twist along the two circles in S3. Okay, so I'm going to come
JZ and JZ bar.
JZ and JZ bars. I'm going to turn on chemical potentials for the R charges in the two SU2s. So I'm going to pretend that I can factorize these, but they're technically not factorized because as I go around, everything is twisted around the same thing. This is the T4, and this is all the bosonic stuff. This is all straightforward. The SL2 partition function we wrote down. The SU2 partition function is something that you can just squint at the yellow book and try to find it, but it's some theta function which you can write down. And this comes. Let me just say what it is for a second. So there's some numerator factor, and then there will be theta 1 of the chemical potential and T mod square. Okay, but because of the twist, this is also twisted with these labels which are NM labels. Okay, and then there's some other factor here in the numerator which makes it modular invariant, etc., etc. And it's important here that there's the spin sum. The spin sum is there because I'll tell you the algebraic reason, and then I'll say why is there a spin sum. So if you look at the SU2 current algebra, you can start with a state which is highest weight state of SU2, and this is annihilated by J0 plus. And then I can use J0 minus to bring it down and construct the spin J representation of SU2. But I can't go too far because there's a bottom to this highest weight representation SU2. And there's a corollary, so 2J plus 1 times, if I add to J0 minus, I get a null state. But there's a corollary to this, which is that J minus 1 plus to the power K minus K plus 1 minus 2J also annihilates the state.
So the second SU2 in Kepler-Witten.
It's the second SU2 in Kepler-Witten, so it's basically the wild reflection of this thing, which means that now this process continues. So in the module built on top of the highest weight states, there are lots of null states. So you have to add them and subtract them and add them and subtract them to actually, like you do in minimal models, to actually write down the thing.
Virasoro, Besumino characters are complicated.
Yeah, and once you do that, that's what there's some theta function way of writing it, and that's what I'm hiding here. Okay. And because of this theta function itself involves a sum over integers, and this comes with states whose weights go like k times m, some m parameter squared. Wait, sorry, this k, yeah, this k is the same as this k is a level of the SU2 algebra. Now, okay.
And the k is there because null states happen at level.
Because of this condition. Okay. And then T4 is straightforward, it's just a Narayan lattice sum, so that's fine. Then there are fermions. Okay. And here we're going to do something which technically I think is, so it's justified post facto, but I'll say one complication that makes it not quite clear why it works. So, and here I should also say that people have certainly studied this partition function. So I think the first person who tried to look at this was Subrat way back in 2007, and then various people have tried to analyze this, but there are pieces of it which are not quite clear to us. In fact, there's sort of prefactors here which you need to get right to get modular invariance correct, and this twisting of the SU2 was not done properly. But the fermion characters, we built them as if they were fermion characters with a standard GSO projection in flat spacetime. So you just take the following, you take trace in the NS with 1 minus minus 1 to the F over 2 projector, and then you take minus trace in the Raman 1 plus minus 1 VF over 2 projector. You can put a minus sign here, that's the difference between 2A and 2B, but since it doesn't matter because of T duality, I'll just put the plus sign here. Now all the fermion characters are twisted because the bosons in SL2 are twisted, 2 of the bosons were twisted, so their partner fermions are also twisted. The SU2 bosons were twisted, so their partner fermions are also twisted. So let's think of one of these traces, the trace in the trace 1 in the Neveu-Schwarz sector. So you will get theta 3 of the same parameter UNM T over eta, that's the 2 fermions. And then you would get a theta 3 of 0 T over eta square root. So that's the SL2 fermions. The SU2 fermions give you and then the torus fermion give you, okay, and then the beta gamma system gives you one inverse guy. Yeah. So if you like, you can basically think of the radial direction in AdS3 and the theta direction in SU2 to make up a light cone, remove them with the beta gamma system, and then the remaining you basically have 4 bosons. And if you take this and basically build a character, then like in flat space, magically it sort of organizes almost into like some kind of Green-Schwarz answer. It sort of looks like it's correctly represented in Green-Schwarz language. Okay, so you go through that exercise, then you get some collection of various theta functions. Now you can put them inside the integral and try to evaluate. Okay. There's an SL2 piece that's common. The remaining oscillators you can just lump into one big oscillator piece and expand. But the thing that's important is that the SU2 piece also has states as currents. The T4 also has currents. Okay. So you need to get everything right. So the thing we did was to basically now at this point, having done this, to organize everything into, figure out how to just basically do the integral, do combine stuff. You have some function of q bar, and then this chemical potentials rho and rho bar. But you can convince yourself, and this I won't try to do because to do that I have to actually introduce something more, that everybody can be organized into n equals 4 super conformal characters. Okay. So before we had SL2 characters, now everybody sits in PSU11/2 characters, which is thus the zero mode algebra of the n equals 4 algebra. And once you've done this, you see first of all that you get the vacuum character of this guy with one caveat, which I'll tell you in a second. And second, you get the currents, which already has the currents from this guy and the SU2, because it has the R symmetry currents. But in addition, you also get 4 free bosons, 4 U1 currents and their superpartners. Okay, that just comes out as a separate factor because that's not part of the n equals 4 super conformal algebra. But you can go further because there are lots of states in this problem which are light.
All the gravity modes.
All the gravity modes, all the chiral primaries. And they have been, of course, computed in supergravity. People have actually done harmonic analysis and written this down. So we should be able to take this partition function and reorganize it to read out that spectrum. And once you identify where the PSU11/2 characters live, then it's a matter of just doing character multiplication table. It's trivial exercise. You just look at it and then you see that things just split up perfectly into the supergravity spectrum.
Sounds like a lot of work.
Okay. but once you do it, it's not so bad. Okay. So you immediately see that you recover the supergravity spectrum and then you recover the states in the
And if you're at large k, there's a nice gap.
There's a nice gap. But again, if you're at k of order 2, this is RNS. So we can't go to k of order 1. We can't go to k equals 1, but you can get to k equals 2. K equals 2 is fine. There's no higher spin currents here. But the sphere basically goes away because its level is shifted by 2. But at k equals 2, you still see all the currents, and you see the analog of the dilaton, which is weight 2, 2. And everybody else is order 1, but there's still a twist gap.
So this was needed, this weight 2, 2 was needed because of the superconformal algebra somehow?
Yes, in this case it's actually part of the superconformal, it's the graviton multiplet. Right. So it better be there, so it's there. So I'll end by saying one small thing, that actually naively if you do this, you don't get the full n equals 4 vacuum character. Okay? And you shouldn't, for the following reason. So in AdS3, if you wanted the graviton character, just summed over boundary gravitons. Right? But what is the n equals 4 vacuum character? The n equals 4 vacuum character, it has some it's a theory, let's say it's an n equals 4 conformal field theory with central charge C. C in the boundary theory is non-perturbative from the world sheet point of view, because C has 1 over G string. C in other words L Planck. I told you that if you have a SU2 current algebra at level k, there are states which are null which have weight k.
Yeah.
K from the boundary point of view C over 6.
So you don't see that.
You don't see that.
Interesting.
Okay. In fact, this is so Guillaume Maloney computed the pure graviton character. Then Rajesh Matthias and Justin computed n equals 1 character, and for low amount of supersymmetry, there are no funny properties of this kind. But higher amount of n equals supersymmetry in 2 dimensions, there are null states which are very heavy of order C. So the character is not some simple object.
Once you start seeing SU2.
Once you start seeing SU2, you have this. I mean, the naive n equals 2 character doesn't have this, but if you impose charge integrality, then it has it. Okay. SU2, of course, you don't have a choice. You have to impose charge integrality.
U1, you're saying.
Exactly. Yes. But there's a way out. The way out is that all these guys are obtained by spectral flow in SU2. Okay. So what are they? So we basically looked at thermal AdS and summed over the supergravitons. But you can turn on Chern-Simons gauge fields at the boundary of AdS. The SU2, we can turn on non-trivial gauge bundles for the SU2 gauge field at the boundary, and then compute a determinant around that geometry. If the Chern-Simons gauge field, it doesn't change the bulk, but it changes energies because it's spectral flows in the boundary. Okay. So if you do that spectral flow up to small footnote, which I will not say now, you can actually argue that the spectral flow commutes with this action, so you can actually reproduce that.
I didn't understand. So you want to get rid of some states, right?
Yes, but you see the way to do it is basically start with so there's one way to get the full answer, the n equals 4 character. So the n equals 4 character is sum over integers, and then from the boundary point of view it's C over 6 m squared. But I can so what I get from supergravity is m equals 0 term, because that doesn't have large energy.
Okay. Are there some minus signs?
There's some the energy is positive, and then there are minus signs in the R charges. In the R charges.
No, but in the coefficients.
Yes, the coefficients are SU2 characters. The
minus signs.
Minus signs. Yes.
Yeah. So this is what I wanted to understand. I want to understand how you're getting rid of states. So what you're saying, if I understand right, is
yes.
if you just do naive canonical quantization
yes.
around your AdS,
yes.
you have more states than you should.
Yes, but basically the way to get the other guys is to look at other saddles.
And so the other saddles will kill states.
Well, but there's a way, but there's a way to write the answer as a positive sum.
Finally, after
you kill them.
But this is what I want to understand. Usually, if you enlarge phase space, you get more states.
I know. But in this case, the short answer is that
something funny is happening. Okay. Very interesting. Very interesting.
Okay, this part has been understood in supergravity by Krauss and Larsen long time ago.
By who?
Krauss and Larsen from 2005 and 2006. So we can sort of repeat that exercise for the string worldsheet. So, I want to say something important here. The reason this is important is that without getting this n equals 4 character, you cannot compute the analog of this for the BPS black hole. Okay? Because the BPS black hole gets contribution from all saddles. And in this asymmetry, in the BPS limit, it gets actually contribution from two saddles, m equals 0 term and m equals -1 term. And they're important because naively, otherwise the index doesn't seem to be independent of temperature. Okay. So I can elaborate on that later, but the short answer is the T4 calculation just works. We sort of see what I said pre-stage at the very beginning, and we can reproduce the index. One nice thing you can do here, which I don't know if has been done before, but something which is worth pointing out, is I didn't say when I wrote down these fermion characters, you should have stopped and asked me, what are my fermions doing in space-time? They're thermal circles, so I had a choice of boundary conditions in space-time.
You're preserving supersymmetry, I suppose.
The way I've written it, I'm preserving supersymmetry,
yeah.
Right? But I don't have to. I could write down the same answer with what usually is called the Attic-Witten boundary conditions, where I put thermal antiperiodic boundary conditions on fermion and some with Attic-Witten phases. But because I turn on SU2 chemical potential, I should be able to interpolate between the two. In fact, this is a nice way to motivate the Attic-Witten formula in this example. You just write down the fermion character in one way and then show that if you turn on the SU2 chemical potential to the right amount, you will actually recover the Attic-Witten phase.
The normal GSO projection
continuous smooth sine GSO projection.
Yeah.
So of course, Attic-Witten didn't derive it that way, but in this case, you certainly can. Okay.
They got it from modular dynamics. Is that it?
It's the same argument because the phases here basically, they got it by saying this guy, and this guy mix under modular transformations. Yeah. This guy is the odd guy out. It doesn't sort of do anything. It's invariant by itself. And then they figured out science tracking how they go.
You've got this thermal boundary condition.
Yeah.
Fixes everything.
Exactly. But we don't have a modular invariant answer for any SU2 chemical potential, so it has to just interpolate. So it's a nice formula in that sense. Okay. Let me stop here. I'm happy to say what doesn't work in K3, but that will require me to get into the weeds of the discussion.
Okay, great. Questions, comments? Is there a Zoom audience? We'll see. Okay, questions, comments? Okay, so maybe we can continue with more questions over the next.
Sounds good.